So up next we have William Farrell. Or Farrell, sorry, I'm probably mispronouncing everyone's name. I apologize in advance. I'm dyslexic, so reading names is always interesting where I end up putting different vowels and consonants. So I apologize right away, and please correct me when you get on. But will be talking about the complex plasma environment at the Wake Formation region along the Terminator. So take it away.
Oh, you bet. Yeah, no problem. Will Ferrell, I answer to anything, so don't worry, Alexa. Um, uh,
Thanks.
yeah, what this is going to be is a review talk, really over about 14 years of work that we've done as part of the NASA Lunar Science Institute and SERVI, the Solar System Exploration Research Virtual Institute. And they fund teams and a number of teams on SERVI look at the solar wind and plasma interaction with the surface. And in fact, you'll be hearing from other SERVI team members later in the talk. OJ Tucker and Liam Morrison will be talking about solar wind implantation and sputtering effects. But I'm going to be talking about here about really just how unique the region at the terminators are in terms of for study and also for exploration interests. And in particular, we've known about the lunar wake for a long time. Really since the since we started making flybys of the moon in '67, we knew that we discovered the wake, Explorer 35, seeing a diamagnetic effect in the magnetic field, and also a dropout in the trailing wake region with a dropout in plasma, a significant dropout. And in fact, it was thought that the edges of the lunar wake, the wake flanks, were actually tangential discontinuities where plasma wouldn't enter, and then those discontinuities would merge up downstream to form a shock. But with more modern instrumentation, we actually found that the ions and electrons could flow in, like the wind solar wind experiment in '94 flew by the wake, made a passage 7 lunar radii downstream. Sure enough, ions got in, although they were greatly depressed in density, about a factor of 50 down to nominal solar wind values. Electrons got into the wake as well, so it wasn't a tangential discontinuity. In fact, the electron temperature actually rose up in the middle of the wake. And actually, the ions that flowed in the form of counter-streaming ion beams. So certainly not tangential discontinuities. In fact, the wake resembled more like the kind of wake that people found trailing behind the space shuttle. It was an ion sonic wake defined by the ion sound speed. And the idea is the following. Imagine you have a plasma vacuum interface. What would happen is, because they're higher thermal speed, the electrons move into the vacuum ahead of the ions and create an ambipolar potential, or an ambipolar electric field that really kind of accelerates the ions into the region to keep up. And as a consequence, the density is a function of this potential, and the potential becomes increasingly negative the deeper you go into the wake. And there's a number of different people who have formalism on this. Actually, Farrell has an interesting non-neutral formalism who found that this electron extension region, electron cloud, actually propagates in. Other people have done more hybrid approaches where they have it quasi-neutral. Actually, Jasper Halekas in his PhD thesis did something rather interesting by using a kappa distribution and found that the electron temperature varied as a function of this potential, and actually could explain the increased electron temperature in the wake. And Chu and all actually had looked at these wake expansion and compared favorably with Artemis. In fact, that's our Chu and all that. That's was our previous speaker, Xiaoshu Chu. And actually, Jasper and Xiaoshu would tell us that the expansion tends to dominate the interface. The IMF kind of guides the expansion. And again, this expansion scales as the ion sound speed, which means that it's self-similar, which means it can occur at other scales. And that's actually an important point as we move along. Let me see here. There we go. Now, just as an example of this wake, here's Lunar Prospector, 6,000 low altitude lunar orbits. This is from Jasper Halekas' thesis back in 2005. And what you're looking at here is the anti-solar point. So at 100 degrees longitude and 0 degrees latitude, you're actually looking at the anti-solar point, looking night side on the moon, and you can see that this the wake forms like almost like a cylinder with a much lower, actually 1/300th of the nominal solar wind values. And if you actually include surface potential effects, you could actually drop that down to even below 1/1000th of what you get in the solar wind. So the lunar night side is a plasma starved region. And Jasper, by looking at the electron energy spectra, the shift in the energy spectra, could infer the ambipolar potential. And he was getting values around, minus 200 to minus 300 volts as you cross through the wake region. So that's, these lunar prospector results went down to about 20 kilometers or so. So you have to yourself, what do you think is happening right at the surface, right at the place where the wake first forms? So if you think about it, what's happening is the solar wind is flowing quasi-horizontal across the surface at the terminator and in the polar regions. And then you're going to have an obstruction, a mountain, a crater. And what's going to happen, because of the self-similar nature, you're going to have what we think is another mini wake forming with an ambipolar electric field, an electron cloud like we just discussed, and ions then deflected in. Now, unfortunately, we don't have modern day plasma measurements of this kind of an orographic effect, but we could certainly model it by modifying the 1D plasma expansion equations that people have had into 2D by including the fact that the solar wind is moving at the solar wind velocity downstream. So you can basically use time to indicate a position delta x and a downstream delta z in depth. So as an example of this, let me see here. Here's the plasma potential, this ambipolar potential that we modeled for Shoemaker Crater for a solar wind flow that's coming in from the left. And of course, the more negative values indicate that you have a dropout in plasma. There's a plasma starved region. That's because the density goes as the exponential of that potential. And again, you can actually use LRO data to make maps. And here's an example of some maps for solar wind flow. This is for Shackleton Crater up near the South Pole. It looks an awful lot like illumination, but it's really not. It's actually surface potential. Where you're getting sunlight, you're getting photoelectron effects, which generally charge the surface positive, which in this grayscale is more white. Whereas where you're in the trailing wake region, mini wake region, you tend to get more negative values, which in this scale makes it more negative. So this actually looks a lot like illumination, but it's not. It's actually potential, and you're getting surface potentials in regions downstream of the topographic features. And of course, when in the regions that are dark, where you have the negative potentials, that's actually where you're getting a plasma dropout, plasma starved regions. Now, one thing that we did is in around 2011 or so, my colleague Mike Zimmerman up at APL, he did a series of plasma simulations on this plasma expansion. For example, he looked at how plasma would expand into a crater of 500 meters in size. So, and what you're showing here is the net charge. Where it's pinkish, that's where the electrons are getting into the wake. You can see the ambipolar field, which are deflecting the ions. And he did 3 cases: no surface, surface charging without secondary emissions, and then surface charging with secondary electrons coming off the surface. And in particular, you could see that you get strong negative charging, surface charging. It's actually, if you don't have secondary electron emissions, it's very strongly negative. With secondary electrons included, it's less negative, but it's still negative, below minus 100 volts or so in potential. And again, there's a plasma starved region here in the just trailing this 500-meter obstacle. Our postdoc, Dove Rhodes, a few years ago did re-examine these 2D expansion fluid equations, and again, looking into Shackleton Crater, again found strong negative potentials on that leeward edge downstream of the flow. The electron cloud region forming, and of course, lower density plasma by like a factor of 100 or so. Actually maybe even below 100. One thing he could do with his model is he could do a lunation average. Remember, the angle of attack here is for the solar wind at any given time, and as the moon rotates, you'll get different angle of attacks, and he could actually calculate a lunation average influx into the craters, and he could actually use that to model for sputtering. So in this case here, he's looking at the the lifetime of an ice layer, half a micron ice layer, um, uh, using his solar wind influx calculations. And even though there's less plasma getting into these craters, there's still enough to get rid of this of a micron-sized layer of ice on the order of 10,000 years. So by solar wind sputtering, you can actually start, you can, in a sense, destabilize any surface ice there on the in these cold traps. But an application more relevant to this talk is charging, and in particular, as astronauts and rovers walk over the lunar dust, lunar regolith, they'll tribocharge. And tribocharge is really just a fancy name for charge exchange upon friction, kind of like walking on a carpet when you charge up. On the lunar day side, this was not really an issue because you dissipate so fast. And so you can think of this tribocharging in an astronaut's boot as a capacitor. And once they charge up, they can either dissipate to the ground or dissipate to the plasma. But on the moon, the ground is a really poor conductor, so you're more likely to dissipate to the medium, the plasma medium. But you can see what happens when you get into these plasma-starved regions. You might not be able to dissipate the plasma faster than you collect it by tribocharging. And my colleague, our survey colleague, Talana Jackson, back in 2011, looked at this. She did a dynamic charging analysis on a boot and considered what would happen if when an astronaut would scuff along the surface every 10 seconds and every 2 seconds. And of course, if the astronaut is exposed to the full solar wind and photoelectrons, very quick dissipation of that charge. And that's why this was never really an effect on the day side. However, once you get into those plasma starved regions, you start talking about 1% of the solar wind plasma and 0.01% of the solar wind plasma. You can't dissipate that boot quicker. Astronaut steps, and this is only in shadowed regions, away from in the wake regions and shadowed regions, not out in the day side. Okay, so this is
2 minutes or so left.
Okay, thank you. So this is an effect we have to think about for the astronauts as they move into as they head into shadowed regions, like people are thinking they should in the Artemis mission. Same thing for a rover. A rover tire, Jackson et al. 2015 found that a rover tire can charge up strongly negative in the night side regions and in crater regions. Of course, on the lunar day side, no problem. The wheel could very quickly dissipate. But there's over a factor of 1,000 difference in environmental plasma flux between the day side and the shadowed regions and night side regions. Drilling is the same thing. More recently, our Dream 2 postdoc, Dove Rhodes, found that a drill can generate 1 to 10 microamps of charge per second, just by drilling into the regolith. And the local plasma there has to be enough local plasma to supply an equal and opposite charge to offset that charge buildup. Otherwise, you're going to get a progressive buildup on the drill and lander system. And so he had a paper in 2020 about this. So there's a lot of weird things you have to think about when you head into these shadowed regions that you don't have to think about as much when you're in the unobstructed solar wind and on the day side. So to conclude, I think I'm hoping that the leads of this conference will conclude that we need to maybe designate Terminator and polar regions as special plasma regions. The planetary communities does this, for cold traps, because the cold traps are, at 25K and are special chemical regions because they contain the volatiles, possibly over the lifetime of the solar system. But in the heliophysics community, the region at the Terminator and the polar regions, that's the origin of the lunar wake, where you have this at some point, probably a perfect discontinuity between plasma and vacuum, and then it starts to expand in. We expect strong spatial variations in the surface potential. We expect human systems to charge up, but to verify this, we definitely need to get a plasma spectrometer in and around and through the Terminator regions, preferably in the polar regions. Maybe the astronauts could drop it off, but one that's sensitive to flux levels about 1/10,000 of the solar wind flux levels. And if we had this, this will provide us key engineering knowledge on the plasma environment so that we can use sound practices and engineering to our human systems. Now, I don't think this kind of thing is a showstopper, but I think you need to do things like maybe have dissipative spacesuits, and think about walking and stopping, roving and stopping. Let the plasma dissipate. There are ways around this, but we need to consider. We need to quantify it and then realize how to remediate it.
Yep.
Anyway, that's it.
Thank you. Thank you. We're a little bit out of time, so I'm going to take a point of privilege as the chair and ask one quick question, and hopefully you can provide a quick answer. You talked about this in terms of the solar wind, but when the moon is in the tail region, the far reconnection line might be out beyond the moon. And so, do you see during geomagnetic storms and times when you get plasma flow coming in towards the Earth in the tail, do you see a similar kind of effect on the other side?
Possibly, possibly. We have not really looked at what would happen in a strong flow in the tail. What we have looked at is what would happen if a CME passed and the tail scooted out of the way so that the full moon, which was in the tail, is temporarily out in the solar wind. But yeah, that is a good question. What happens if you get a strong flow? Probably you develop a wake as well, but it's probably not as sustained.
Mhm. That would be interesting to know how magnetospheric weather and not just the solar weather might end up impacting Artemis and the different technologies we plan to put there. So thanks so much.